So the analysis in R would work as follows then. So the basic commands to read the data in are given there under the first bullet point. So the idea is that you should need a comma and a space between each observation. Put the data in brackets, and you need the letter C there to act as a concatenation, literally binding all the data together. And then the next step you do in the second bullet point, introduce a squared term for year. So I've just put there, year SQ goes to year squared. Squared is done using this sort of upside down hat character. And then there are, as it says there on the slide, some equivalent R commands. So .lm for linear model, .glm for generalized linear model. Now I will go through this a little bit more in my module in the second semester. Okay, but whilst these two commands should give you the same answers here, if you have a larger data set, actually the .lm command should be computationally advantageous, so please use .lm rather than .glm for this. Okay, so similar to it as you've seen before, and because it's such a relatively simple data set, you can just enter the data straight in on the command line. You don't have to particularly read this in from a .text file. So the first thing to do here would be to plot the data over time. So how you would do this is the plot command in R, and then this has to act on the X variable first, then the Y variable, specify the labels for the axes. So the X lab here would be year, and then the Y lab would be the percentage of divorces due to adultery. With that you get sort of strange labels and label titles for the axes, and then if you plot this, what you have is a sort of general decrease over time, although the divorce rate caused by adultery seems to be very low in the first year. So rather than the initial sort of interpretation in the newspaper, which was the divorce risk peaked in the second year, then decreased thereafter, really I think it's possibly safe to say that the divorce rate is unusually low in the first year and then decreases steadily over time. So I suspect what you have with this data is the first observation is artificially low, probably caused by some sort of legal reasons, and then after the first year you see that this divorce rate does steadily decrease over time. Okay, so it's a slightly dibbly-dobbly example, but I think there's some suggestion here that if you're not careful, you can make some interpretation mistakes. So the analysis in R then, so to fit a linear regression model, this is just the simple two-variable regression model. How you would do this would just be M goes to linear model with the percent related to year. So call it something simple, and the tilde sign there means that the percentage of divorces caused by adultery is related to the number of years of marriage. And the regression model is the same basic set of commands. So call it something simple here, b.lm, make sure it's not the same as what you've called the first one. So it is different. We've got a.lm is the first one, b.lm is the name for the second one, and this is just a linear model where the percent is related to both the year and the year squared. And again, you've got a sign between the different x variables to sort of join those together in the right way. Note again that you've got this separation in R between doing the computation and displaying the results. Okay, I always describe this as think R for robot. It will do exactly what you tell it to do, nothing more, nothing less. So what you have, if you look below the second bullet point, is the computational command. So b.lm goes to this linear model. Second separate summary command, their summary b.lm, to actually display the results of the regression. Use this summary command, an abridged version of the results is shown below, and the idea here is that you could use the t-statistics to test to see if this additional quadratic term is needed in the model. Okay, so this is the table of t-statistics, and again the default when you're doing these sorts of regressions is to usually include an intercept or constant term, so it's the second row downwards of the table that are important here. And then if you look at the red row, see that the p-value is non-significant precisely because 0.3943 is bigger than 0.05. Some suggestion here that the quadratic term is not needed in the model. Now the situation can become a bit complicated here in that the variable year is non-significant at the 5% level but borderline significant at the 10% level. Now probably what would happen is if you refit the model without the year squared term, then this year term would then become significant and this apparent paradox would resolve itself. Okay, so I'll go through that a little bit more in the lecture later on. Okay, but for the moment there seems to be some evidence that the quadratic term is not needed in the model, and alongside that the suggestion is probably that the original analysis in the Daily Mirror is mistaken. Okay, so a slightly doubly data example, but if you're not careful you can make simple interpretation mistakes and publish them. So probably the best way to sort of test for this is using an F-test rather than just relying on the t-statistics, because there are problems with multiple testing. So what you would do in this case is use the ANOVA command that we mentioned before, and this has to operate on the first linear object and then the second linear models object, and then specify that you want to run an F-test. And once you do this, this is the version of the results, and you have here that the p-value in this case is 0.3943. So you get the same interpretation in terms of the F-tests and the T-tests. So the analysis here suggests that the quadratic term is not needed in the model precisely because p-value here is bigger than 0. So the interpretation of this would be the information or the extra sum of squares provided by the quadratic term is not statistically significant, is no bigger than could occur by chance. So there's no evidence really that a curved line fits the data better than just a straight line. Okay, and again this is giving us some statistical evidence to suggest that the original analysis interpretation is misplaced. So if you just restrict to the two variable regression model and summarize those results, you get an abridged version of the results on the top half of the slide. So in these tables of t-statistics, the thing to look for here is the second row of the table downwards where all the action is, precisely because again the default choice within regression is to automatically include an intercept or constant term. So if you look at the second row, what you see here is that the coefficient of year is significant precisely because the p-value at the end is less than 0.05 and you've got some asterisks at the side of this number. The thing to point out here is that once you get rid of the quadratic term for year in the model, then the coefficient of year is statistically significant and negative. The statistical significant bit is the important thing here, and then how you interpret this is slightly the opposite way of how you work this out. So you work this out by saying it's significant and then the thing is negative, and then I've interpreted this here. The coefficient of year is negative and statistically significant precisely because the p-value is less than 0.05. As the number of years marriage increases, percentage of divorces caused by adultery decreases. So I think there's some suggestion here that Daily Mirror analysis is misleading. Safe to say divorce rate is unusually low in the first year. So I wanted to talk about regression modelling assumptions. Now these are discussed in chapter 7 of Gujarati and Porter, but my list is more complete, and what I would say here as well is that rather than Gujarati and Porter, I am the one who's going to be marking your assessment. So this list of regression assumptions is important for two reasons really. So firstly, it's an easy thing for me to sort of set on assessments for both exams in the days when exams were a thing and for individual coursework projects, precisely because what you have here is technical detail that isn't purely quantitative in nature, and I think that's something good to sort of examine people who are wanting to specialise in accounting and finance. So I think this is an opportunity here for people who are into accounting and finance who want to demonstrate analytical skills and attention to detail to do well in this course, even if they don't like equations and numbers. And the second thing to point out is that these regression modelling assumptions, if you can sort of verify these on your dissertations, and that is becoming very quickly towards the limit that you can reasonably expect MSc students to be able to achieve. Okay, so there's two reasons for this. So it's a good thing to sort of set on assignment sometimes, and also if you can master these, useful for dissertations. Regression models is completed there. So this isn't quite the same list as used in Gujarati and Porter. Now, I'm sometimes a little bit rude about their book. They do have a good choice of topics, but I think their treatment of regression modelling assumptions is quite poor and quite imprecise. I think this is sort of symptomatic of wider problems with econometric textbooks, and that they're sometimes not very clear about the modelling assumptions that they make and tend to emphasise applications. And this is sort of understandable and fine for teaching material. I just worry that this lack of precision might lead to problems later on if you're doing more advanced study. So as said there on the slide, may lead to significant problems when undertaking more advanced research outside the scope of your MSc course. Okay, so this is a details thing. I'm not going to read the slides out for you, but it's certainly, I think, worthwhile bearing this list of regression modelling assumptions in mind. In the past, when I've set written exam questions, I've asked students to essentially memorise this list. When I've set courseworks, I've also asked questions on this list. My plea to you would be that if I set something on the coursework related to this, please don't leave this question blank, because it's probably relatively straightforward to answer. So these list of regression modelling assumptions lead to a sort of quite well established list of conventional countermeasures. So the first one should just be relatively straightforward from the formulation of the model. The second one might be violating some time series problems, but is largely outside the scope of the course. For point 3, the fitted residual should automatically have a zero mean. Today's lecture will deal with heteroscedasticity. Point 5 may be remedied to some extent by trying to model log y instead of y. We'll go through that in more detail later on in the course. Point 6 is answered actually in lecture 5, not lecture 4. Point 7, this occurs in certain specialised bioinformatics computer science problems, but is outside the scope of your course. But I did want to clarify here that this is quite a big area of research, even if this isn't possible to sort of do it justice in a course such as this, and if this is something that is completely overlooked by the original textbook reference. Point 8 is answered in lecture 6, and then point 9, really that's outside the scope of the course, but what this is hopefully trying to do is give you good habits, and the idea is this might be solved to some extent if the models and the analysis used are derived from an underlying theory or literature review. So in this lecture we will discuss heteroscedasticity. So the classical linear regression model is the equation below. So what you have here is that y is related to a set of x variables plus some random error, and in particular the classical linear regression model assumes that for each observation I, the variance of this random error term is constant. So the variance of the random error term is just completely the same, they're all the same, and this equation 5 defines something called homoscedasticity. So it just means that the randomness associated with all the random errors is exactly the same. Now if this equation does not apply, then you have something that is instead called heteroscedasticity. So homoscedasticity, all the variances are the same. Heteroscedasticity, at least one of the variances is different. Okay, now we'll go through the sort of countermeasures for heteroscedasticity later in the lecture. The reason why this is important is that if homoscedasticity doesn't hold, this is the assumption that underpins all the theory and all the background bits of maths behind the programming. So you can still run the regression model, your laptop is unlikely to explode, but you may not be able to trust the regression results that you obtain.